Yes, we can hear you. Just share your
Fine.
screen and you can start.
Yes, yes. So thank you very much for the invitation, and let me see if I can manage to. So I will try to put in full screen. It's even better. So right. So here is my presentation. I apologize for not being able to be there, which I would have been pleased to, of course. And let me say that
It's a little low
perhaps
now.
sorry.
Little far away now. The
A
sound.
little bit, a little bit, yes. Problem is that we have the term which just started, you see,
No,
and
I mean the
so
sound, Professor. Sorry.
yeah, okay. So the thing is that I want to point out is that maybe there is not much quantum gravity here, but perhaps some aspects of our work, of our research program on neutrinos, of which this is a recent aspect, this of the equivalence principle evaluation, may be of interest, and I will try to emphasize this aspect. So let me go to short summary of the main thing is an approach here of neutrino mixing and oscillations in quantum field theory that we have been developing over time, and which has many interesting aspects. I will try to pick some the most relevant for this audience, perhaps. So one is um, consider neutrinos as unstable particles. I will show in what sense. Another is the quantization of mixed particles in accelerated frames, which has, of course, to do with Orlo effect. And then this the topic of this talk, but it's just one of the derivations, let's say, of this line. And then, if I manage, I would like to say a few words about chiral oscillations, where we have some work going on, which with recent results, which I think they could be interesting. So if I manage in a few minutes. Okay, so our let's say, I mean, motivations for the study of mixing are quite obvious. Perhaps I should emphasize that we have an interest in the theoretical aspects of this problem, and some of these how to say problems emerged in quite early. We were actually unaware when we this was during my PhD. We published this work, which is down here. But people realized that soon after, I mean, after some time, soon after Pontecorvo theory, which of course is formulated in quantum mechanics, they was clear that there was some issue, some problem. Maybe the first understood clearly is Mannheim, Philip Mannheim, and then Giunti and King, they made this explicit, and they found, let's say, their solution, but I will discuss this. So what is the problem? The problem is, I mean, if from the point of view of Pontecorvo theory, there is no problem, of course. This is a well-posed problem, I mean, in which you have a superposition. Apart from the fact that in quantum mechanics, superposition of different mass states would be forbidden. But let's forget this mathematical point, and this is called the Bargman superselection rule. But in any case, this works very well and fits the experiments, what is most important. And so you have in the sample two flavor case a superposition of mass eigenstates, and the evolution gives you the probability of transition or survival. Right, but the problem is that standard model is formulated in terms of fields. So the point is that, let's say, look at the lepton sector. We are looking here at the lepton. The Lagrangian, if we put the mixing on the neutrino side, could do otherwise, but this is conventional choice. Then, of course, the mass term for neutrinos, assume they are Dirac. I mean, we can do for Majorana the same thing. Is not non-diagonal, okay, in the flavor. But the interaction is diagonal in the flavor. So the point is, we can diagonalize this, but once we diagonalize, then the kinetic part, the free part of the Lagrangian is free, free Lagrangian and is diagonal in the masses, but then the interaction term is not anymore diagonal. So it's clear that there is a problem in the definition of the state which we have to put in these amplitudes which we want to calculate. And Pontecorvo states, they don't fit here. You can easily see. This was realized also by Giunti and Kim. And they proposed a model which is called like external wave packet model, where one substantially hides the neutrino in a sort of internal line of a gigantic Feynman diagram, which it may work, but we will show why it cannot work. Fundamentally, I mean, for experiments, all these differences are very small and they are not yet testable. So what we did is to consider the quantization, canonical quantization, or can do also impact integral, of mixed fields. Let's take for definiteness 2 Dirac fields with different masses. So you see, this can be tackled algebraically because you can write the generator of this. It's just an element of an SU2. And then, okay, if you calculate this object with, and you plug in the expansion for the fields here, for the free fields 1 and 2, you discover that this object does not annihilate the vacuum for the free fields 1 and 2. So it's a bit strange a situation because we have the vacuum for the flavor fields, which is in the infinite volume limit orthogonal to the one for the massive fields. This orthogonality has to do, boils down to orthogonality of U and V wave functions with different masses, which is an obvious fact. This is a situation which is not strange in some sense, because in quantum field theory, it is well known that the Stone-von Neumann theorem doesn't hold, and inequivalent representations, unitary inequivalent representations are allowed. So we are exactly in this kind of a situation. So if we open such a vacuum structure, we find a complicated condensate structure, similar in some sense to BCS, but of course with more structure. And we can see also, very interesting, the condensation structure, the condensation density has a scale, a maximum, which is at the square root of M1, M2. This is in the momentum, with respect to momentum. This is the Bogoliubov coefficient. Right, so how annihilation creation operators are done for this? You see, they are partially what expected, partially not. I mean, the black part is just the Pontecorvo, what would generate the Pontecorvo state, and then we have a Bogoliubov part hidden inside here. And this is not, it's irreducible, you cannot really disentangle. What you can do, these are the Bogoliubov coefficients, so everything is okay here. You can check also for bosons. I mean, we did all sorts of generalization. So what one can do, however, is to write down in terms of the annihilation creation operators, the generators of these two transformations, the one for the Bogoliubov and the rotation in terms of, and then check that the generator for the fields, you see, is a sort of non-commuting combination, because if B and R, they would commute, this would be just R. So the essence, the take-home message is that Pontecorvo and Bogoliubov don't commute. That is what we found, basically. And then, right, but then what this has to do with oscillation? How we derive oscillations in this picture? Well, here we proceed in the Heisenberg picture, and we look for observables associated to the oscillation. So we look for a flavor charge. So if we look at the Lagrangian, let's consider just the free part. For two free fields, this is trivial. I mean, we can also play with an SO2 transformation, but just we have a conserved charges for the field 1 and 2 separately. Right, if we repeat this for the same Lagrangian, but in the flavor basis, because now we want to create an excitation which is defined having a given flavor charge in the vertex. Okay, we find that these charges are not anymore conserved, of course, because they are time dependent, they don't commute with the Hamiltonian. And you see, they are quite complicated combination of the fields with definite masses. So if we look for the eigenstates of these charges, it's not so obvious here, but if we plug the operators we have found before inside, they become diagonal. These are the charges. And when we plug these complicated operators here, the charges are diagonal in these operators. Here, okay, we redefine, we subtract some vacuum energy. And so we can define the neutrino state with the definite flavor, and of course massive and mixing, in the vertex at a given reference time in the Heisenberg picture, and then calculate the expectation value of the flavor charge operator on this state. And what we find is very simple, it's just algebraically exact. So you have the Ponte-Corvo formula, which is this one in black, plus corrections, and the correction which goes like the sum of the frequencies. It's very similar to what you would obtain with two harmonic oscillators coupled. Okay, for bosons we get something similar. Of course, these coefficients, they are negligible. This is 1 in the relativistic limit, and this is 0. So Ponte-Corvo formula is okay for relativistic neutrinos, but it's not exact. So this is a formula which is exact, at least in the context we consider. So now, why Ponte-Corvo states are not good? Because they are not eigenstates of the flavor charge. And the same is for the Giunti approach, because it's based on the vacuum, which is not correct. So the propagator in that case is taken, although it is an internal line, it is taken on the wrong vacuum, strictly speaking. I mean, differences are more. But we proceed, we want to understand really what is going on there. This is our methodology. So we have all sorts of other results. I don't want to. Let me just detour a little bit for a minute and show that actually this is also something we noticed at some point. This combination, we consider Ponte-Corvo, I mean, is sufficient, is actually an entangled superposition of states. It's not just a rotation within some Hilbert space. Why? Because you see, there is a natural hidden product, tensor product structure in this Hilbert space for the masses 1 and 2. This you can understand very easily. I mean, these particles are excitations of field with different masses, and these are orthogonal, these fields, these Hilbert spaces for different masses. This is a well-known result. Basically, it's Hugg's theorem. If we go on the other end, if we look in the flavor basis, our qubit then are these objects, then you see that entanglement here is generated in the course of time evolution, and the entropy can be calculated as product of probability. This is the linear entropy, it's just a monotone of von Neumann entropy. So we did this, it's quite interesting. Actually, a lot of work stemmed from this, and there is a quite big activity of looking at quantum correlations, in general in particle physics, but neutrinos are quite interesting because possibly in the future they are relevant as carriers of quantum information protocols beyond the photons. And so, for example, I showed just you what we did recently using the complete complementarity relations. We have tested for realistic parameters of an experiment, one of these long baseline experiments. We have tested all the properties of the quantum probability. This is quantum score. This is the oscillation probability. You see there is a rich structure of quantum correlations in the hidden in a very simple system like this single party system. Right, but let's go back to our original problem, no? So we want to understand what is going on in the vertex. So we know now that, and this is a fact, this is quite easy mathematically it was confirmed by other calculations. Since we know that mass and flavor representations are unitarily inequivalent, okay, now what is going on there? Which one is the correct one that we should use? So there is a problem of choice, clearly. So I represented in this way that we can ask to iterate this question. Okay. So how we can tackle this? Obviously, we could do an experiment. We cannot do for the moment because this is these effects are relevant for non-relativistic neutrinos. We have predictions for, apart from the oscillations, also for the beta decay endpoint. Also in these quantum correlations, there are modifications which are very small coming from this quantum field theory structure. On the other hand, we also could use a more sophisticated way, trying to use the formal consistency of quantum field theory. And here comes the discussion of these effects in non-inertial frames, and to look at the consistency of the theory in some situation that I will explain. We have done this in these papers. On the other hand, if we if we accept, as we do, the fact that the flavor neutrinos are the fundamental entities, then we have to take also the consequences of this. Like, for example, the issue of Poincare invariance, which I will not discuss. So we did collaborators here some time ago. And then the evaluation equivalence principle, on which I will say something in a while. And then flavor energy uncertainty relations that I'm going to show now. So what is why we talk about time energy uncertainty relations of because they were actually introduced in the case of neutrinos to give a motivation, to give a condition for the existence of flavor oscillations. Because you see, if in the vertex the energy is completely defined, oscillations, they cannot take place. This is very clear. The other thing is to say that what goes out of the vertex has non-definite energy, which is what we imply. But the Mandelstam-Tam uncertainty time energy uncertainty relation was introduced in this respect. So how it works? It works that we need a clock observable because we cannot measure time, of course, directly. So this is the original thing. So what is a time observable? I mean, it can be a pendulum for Galilei, or maybe a neutrino. Okay. So in our case, good time observable is naturally the flavor charge. So this is two lines. We have derived this, and we get this relation, which in fact correctly reduces to the one by Bianchi collaborators. However, is for relativistic neutrino. However, it's the interpretation which is different. So here we are sort of implying that these flavor neutrinos, they do not have definite energies. They are not representations of the Poincare group. This is our conclusion. On the other hand, this prompted us for an interesting approach, which we carried on with colleagues, and Giorgio is here in the audience. And just to not rely completely only on the flavor vacuum, we tried something which was done by Bernardini, Maiani, and Testa, and also you find described in the book by Saverio, Pascazzi, and Facchi. And so to make a finite time perturbation theory in the interaction picture, not as mathematics, just finite time, and to see what we recover, which oscillation formula. So basically, the idea is that to treat the interaction term, the mixing term, which is trivial interaction term, as a perturbation. Okay. And then when we do this, I don't go into detail. I just say that we get this diagrammatics, and apart from vacuum bubbles that have to be discarded, we find exactly at the correct order the oscillation formula which I've shown before. So you don't find Ponte-Corvo formula. Of course, in the relativistic limit, Ponte-Corvo formula is valid. I stress again. So let's come back to the other issue. I just want to ask if you can hear me, because I don't have any feedback. Sorry, I have a full screen, and so just if you can confirm that everything is okay.
Yes, we are hearing you.
Thank you. So, how we can make a theoretical test of the validity, consistency of flavor neutrino as an assumption. So here we followed the work, beautiful work, I have to say, really. We were very happy to read these papers by Mazzas and Manzella. I will quote afterwards. I'll go in detail, and to see how the consistency of our hypothesis can be checked in a context which is the one of the accelerated decaying particles, namely protons in the case. Okay, so what is the point here? Is that it was noticed quite early that accelerated particles, even if they would be stable in an inertial frame, they could decay in principle. Okay, would need a very high acceleration, but this is not the point. I mean, we just think theoretically here. And so in this series of remarkable papers, Mazzas and Manzella, they have shown that under very simplified but very realistic hypothesis, that if you start with a proton and you accelerate, after a while, this will decay by inverse beta decay. Okay, and this is what already Müller showed. But what appears in the laboratory frame as, let's say, normal decay, on the other hand, in the comoving frame is not so trivial, and it requires to take into account these diagrams, which only arise if we consider Orru effect, Orru thermal bath. So this is the key point, which is very remarkable. And if you do the calculation they did first, and you find the perfect agreement at the level, okay, but then it's interesting, okay, would be interesting to see higher orders of this procedure because maybe they could give surprises. They could give more information on the relation between quantum fields and let's say gravity, I mean, accelerate the non-inertial frames would be quite interesting. Anyway, coming back to neutrinos, this calculation was done, original calculation is done with massless neutrinos, but was then generalized in a quite tour de force, these 4 dimensions, the mass of neutrinos by these authors, and then it works. Now, at some point, Torrieri and collaborators, they realized that maybe the mixing creates some problems here because on one hand, flavor neutrino seems to be favored as an output in this vertex here. On the other hand, it's difficult to accept them as a constituent of the thermal radiation of the Uru radiation. And so, in some sense, they would clash with the thermality, with KMS condition. And so, there was some problem that they pointed out. This actually, we didn't know immediately of this work. We came across after. But in fact, in the same period, with our student Gaetano Luciano, with the colleague Lambiase, we were working on a related problem. The problem is this, the quantization, to extend the quantization of mixed fields to accelerated framework. The idea basically is this. We have found, I've shown before, that associated to mixing, there is a Bogoliubov transformation. So we know on the other end that associated to the acceleration, I mean, when we go to render frame, there is a thermal Bogoliubov transformation. So how they combine these two? So we did all the calculations. I mean, it's very technical, the paper, but you can derive really all the algebra. And what comes out as the most remarkable thing is that these two Bogoliubov transformation, actually, they combine. And the result is that the distortion of the spectrum, the Uru spectrum, which is not perfectly thermal. Later on, we realized with Gaetano Luciano that this form for particular values when delta m square is small, when this parameter is small, which is reasonable, it's really exactly of the form of approximate distribution, Sallis distribution for a small q. So this is very interesting because it works both for bosons and for fermions with the correct sign. In one case is superadditive, in the other subadditive. This we find very interesting. And here maybe there can be something which can go beyond, I mean, what I'm saying here, in the sense that Uru effect and Sallis statistic may be related, I mean, via deformed uncertainty relations, which provide some non-thermality, and they are related, of course, to physics at high energies. So I am referring to the generalized uncertainty principle. So maybe this can be interesting. I mean, namely, the structure I am sort of alluding to the fact that the flavor vacuum may be a result of some interaction unknown that we after all we don't know the mix where it comes from. So this can maybe result of physics beyond the standard model, but this is just a speculation. So what we did is to calculate, to repeat the calculation by Mazzas and Vanzella, and then also they worked on this. I will mention afterward, using flavor neutrinos. So here things get a bit complicated. We get a term, mixed term, which is not easy to handle. But in any case, this is in the lab frame and this is in the co-moving frame. But in any case, we get the equality for the relevant regime, let's say for Pontecorvo states. I mean, the others are too complicated to handle. We have to try numerically. And then we went beyond this because, you see, we could even imagine that the emitted neutrino oscillates. Okay, the emitted neutrino can oscillate. This actually can happen because we look at later time here. So we have to add this term here. And then in the thermal bath, the flavor neutrinos, if thermal bath is constituted by flavor, they have to oscillate as well. So if we plug in these terms, additional terms, actually you get again the perfect equality of the two decay rates. But what I think is more remarkable is that when we extended to 3 flavors, this is now not easy. We did this, and you consider CP violation Then this comes really very nice with flavor neutrinos because comes proportional to the CP symmetry to Yarscough invariant, and it works. So this is a physical feature of the theory that you have to reproduce somehow, and there is no way to reproduce if you plug in massive neutrinos in the vertices. So here is sort of, here is the other paper I was referring to, is by Mazza's group, and of course they did the calculation. It works also with the massive eigenstates, but I think on this last point in particular, it's difficult to do. Of course, I mean, the conclusion of this could be also that nobody's perfect, because you see, also we have to give up KMS condition, but it's a fascinating scenario. I mean, to try to explore the what is going on really ontological, I use this word, by using the consistency of quantum field theory in non-trivial background. This I like very much. And so let me go now to this last topic, and then perhaps I have some time. I would like also to show this topic of the chiral oscillations, which I like very much. So what we did here, well, we did the simplest thing. We took the Dirac equation in presence of mixing. So we have two coupled equations, let's say for electron neutrino and the muon neutrino. We put psi here for some reason. And then we work the non-relativistic limit of this, which is not completely trivial. I mean, we follow the textbook procedure, so we separate. Let's consider just this first equation, because the other is somehow symmetric. You can then recover. We check that everything is okay, exchanging just mu and d. Well, when we do this, we separate. This is the large and the small spin component. This is a bispinor. These are two component spinors. And you get these equations. Okay. So typically what you do, you make some approximation and you try to write the equation only for the large component. So we follow the usual things. I wouldn't go too much in detail here. Just let me show you the essence of this calculation, the results. And there are two papers, actually. We also did the bosonic case recently. So once you do this approximation, you factorize this phase like this, you arrive at this equation. So now, what you can do here, you can take the first equation, you can extract the key from the second, we drop this tilde here, and you get this equation. But you see, still, here again, you have also, again, this popping up this key mu, this small component of the mu field, mu spinor. So, if we go further, we can extract the mu and plug in again, but again you will pick up a key. So it's obvious that this never ends. So the only way is that if there is a sort of convergence here, and by the recursive procedure, and so the equation takes this form. Now we checked that this one is just a geometric series, and this quantity is smaller than 1. So this really converges, you can resum, and you get this equation, Schrödinger-like. So here we see something a bit surprising in the sense that the inertial mass associated to an electron neutrino is not just this ME, but it's a redefined, maybe there is, sorry. Okay, no, so just the time, not a question, okay. I was looking at the chat. So, sorry. So there is a redefinition of the inertial mass. A similar redefinition also occurs for mu. So this procedure, this part actually is responsible for the oscillations, for the flavor changing. This is equal for the muon neutrino if you write the corresponding equation. So right, then we have to add the gravity. We make the hypothesis of weak gravitational field. And okay, we have reasonable hypothesis in which we have isotropic stick situation, and so I skip this. I mean, just the formalism for dealing with spinors. And then what basically happens here? You can do the same procedure again. Doesn't change anything. You can do the resummation, but you end up with this equation. So now here you see clearly that there is a difference, because in the kinetic part, the effective, the inertial mass is still the corrected one, although instead one which couples with gravitational potential is MA. So in this sense, there is a violation. Now, I mean, we have not figured out, we were not able to figure out a possible experiment, thought experiment to evidentiate this point, but we think this is there, and this is there also for bosons. We have worked out recently this. Let me remark one thing. One could think, okay, but why you don't diagonalize the thing? Yes, you can do this, but the point is that then you cannot come back because the two limits, the relativistic limit and the rotation, let's say the Ponte-Corvo in this case, they don't commute. So this really doesn't work. You have to follow this way. So I have, I think, a few minutes, and I would like, if there are no questions, I don't know if, please interrupt me in any moment if you, or I will wait at the end if there are any questions.
You have
So I would
5
like
minutes,
to-
but we take questions after.
Yes,
Okay.
yes. No, I just, if there is some urgent question or some mistake you spot. Okay, so why chiral oscillations? So, okay, if we go back, remember we started with the weak interaction. We said weak interactions, they have charged current. Weak interaction, they have this characteristic that they are diagonal in the flavor. Okay, and so this was our starting point because, of course, then the mass, the mixing term clashes with this somehow. Okay, but weak interactions, they have also another character. They are chiral, right? So imagine you create an excitation with a weak interaction and you detect, again, with weak interaction, maybe a neutrino, but maybe even a charged electron at this point, you would get chiral oscillation. This is a fact which is known from some time. Actually, recently, people realized that this is relevant for neutrinos in the cosmic neutrino background, gives a quite, although, because they are non-relativistic, so this is also a non-relativistic effect. By the way, I want to say, I noticed, and also looking at the transparencies, I have several collaborators which are Brazilian, and a lot really of work here we have been involved with this from Brazilian physicists, so I'm quite happy with this situation that I'm talking in a conference in Brazil. So you see, we did some work with the collaborator with Alex Bernardini and Victor Bittencourt, and on this, within the usual, which is what usually is used, the Dirac equation, and you find the oscillation formula. We explored how the oscillation formula flavor mixes with the chiral, and you get a formula which includes all the effects, chiral and flavor, and recovers our quantum field theory formula. Also, this is independent. This comes from just Dirac equation. By the way, recently, we did another thing. We attempted to describe in quantum field theory this chiral oscillation. This is something it's extremely recent. I put the other month on the archive. So consider this, and this is very much in the spirit of what we have done before. You take just a simple Dirac Lagrange, massive with mass. Then we know there is another charge, which is this one. Now consider the left and right component, which you can do. And of course, the mass term is the one which produces these chiral oscillations, okay? Now, let's ask, what are the charges in the spirit of what we have said before? I mean, we have an interaction which produces a chiral object. So we want the eigenstate of this interaction, of this property, this charge, which is the chiral charge. So we can define these chiral charges. Now, of course, the field is massive. We have explicitly breakdown of the chiral symmetry by the Dirac mass term. We are in the broken phase. Okay. So if you do this calculation, this is really trivial, and you substitute, okay, for the nether charge, this is the result in textbook. But when you do for the flavor, the chiral charge, you find that these terms, they are not trivial. I mean, you have to calculate these terms with the gamma 5. And then when you write the left charge, for example, you have boundary conditions because in the massless limit, you recover the nether charges, which are the charges in terms of the 5 fields. Well, you find that this is diagonalized by Bogoliubov transformation again. And these are the Bogoliubov coefficients. So here you see there is nothing, it's somehow strange that was not looked before, at least to my knowledge. We didn't have, we haven't found this somewhere. So these charges are diagonal in these operators. You can double check because you can put in the field these operators, the inverse of these operators, so you rearrange and define the wave functions, the spinors with definite chirality, and they are combination of those with definite helicity. You see, everything works. Of course, these excitations, they don't have definite energy because they are superposition of particle and antiparticle. So again, we are in the presence of inequivalent representation. So the massive chiral vacuum, which is the eigenstate of the chiral charge, is unitarily inequivalent to the one for the Dirac field. The charged, the chiral oscillation formula is recovered trivially, so it's exactly this result. So this is very intriguing, I find. So it seems that, I mean, you see, we were somehow blaming the neutrinos to have strange properties, but here the point seems that it's weak interactions that they have, they are non-trivial at the level of representation, at particle level. So I would like to conclude with this. So perhaps we should ask question not so much about the neutrinos, but about weak interactions. Okay, thank you very much.
So we have a questions from George.
Thank you, Massimo. This is George Matzas. Glad to meet you, even
Oh,
virtually.
nice to meet you.
Okay.
We never met.
Yeah, we never met. So
Yes.
just one comment and one correction.
Yes.
In 2020, we reproduced neutrino oscillation without using flavor states. So the title is neutrino oscillation without flavor state. So
Okay, so I should put here, you mean?
right, exactly. So
Yeah,
good.
okay.
Now, and in order
But
to
the
do it,
CP, you see, yeah, we checked very well that
we didn't
you cannot
check CP.
reproduce this CP in this context.
We didn't look at CP.
Okay, we should.
The second thing is that, do you agree with the fact that if you, as you said, if you put the mixing in the Lagrangian and treat and use only quantum field theory for massive states, do you agree that eventually, if you are in the Minkowski vacuum, uniformly accelerated observers will see a thermal bath of all particles, including neutrinos with well-defined mass at the Unruh temperature?
This I don't agree. This is the
No, I
problem.
mean,
Because
sorry,
yeah,
just to
the
complete.
point is if the Minkowski vacuum for this mixed particle is the flavor vacuum, then I mean the choice is that one that we have to do. If one disproves that, okay. But then you see, the flavor charge is violated in the vertex at 3 level, which is a problem with standard model. I am open to any
Yeah,
option.
but
This is why I'm dubitative. I'm not ideological. I mean, I would just.
I see. No, I'm
Yes,
just saying the following, that assuming free fields and
Yeah.
massive neutrinos, they may or may not oscillate, uniform accelerated observers must see, according to quantum field theory, plain quantum field theory, a thermal bath of all particles, including neutrinos,
Of course.
if you restrict yourself to well-defined massive mass neutrinos, even if they oscillate. Now, if these uniform accelerated observers decide to measure this thermal bath using a detector tuned to see well-defined flavor, this is another story. They can see different things. But if you have a detector that sees neutrinos
I
with
see your
well-defined
point.
mass,
Your point is about, it's about, excuse me if I interrupt.
go ahead.
It's about asymptotic vacuum. You are perfectly right, because in fact it is a problem to think to asymptotic vacuum as a vacuum which is time dependent, as we find there. So perhaps you are right. I mean, this should be considered restricted to the interaction to the measurement process.
Yeah.
But it's a fact that in the vertex there you must put the eigenstate of flavor charge, in my opinion.
Okay.
Because at tree level, if you will consider loop corrections, there is a violation of lepton charge, but it's extremely small. On the other hand, this chiral charge is very interesting because chiral character, this is exact, this is gauge. There is nothing to do. I mean, it seems to me, I mean, I'm just doing some calculations and I'm very open to feedback, of course.
Okay. Okay, thank you.
Thank you very much. Thank you very much.
We are already a little late. Thank you again, Professor Massimo. Let's thank
you.
Lecturer. We are 10 minutes late to have a